All right, let's go ahead and get started on this. If anyone has a sample exam that has not been turned in, please do it now. Once again, this is 10 points towards your credit that will be added to your point total. Before we actually start on the exam review, I'd just like to talk a little bit about the lab we did. We did paper chromatography. Chromatography is something that's used a lot in like organic chemistry and more advanced analytical chemistry. It involves the interaction between substances with a mobile phase and a stationary phase. Now, this is something like the setup that we had. The stationary phase is a fancy word for the filter paper, and the mobile phase is the water that you put in the bottom. As we said when we talked about physical properties and whatever kinetic molecular theory, we said that every substance has an inherent attraction to every other substance. So when you put a spot on this paper, the chemicals that make up that spot are going to be attracted to the paper. They're also going to be soluble in the water. So depending upon the strength of each of these attractions, the material is going to basically move from the stationary to the mobile and back again and back again and back again. And spots tend to separate then according to their affinity for the paper and their solubility. If you guys have the sample exam, please just bring it up here. Okay, thank you. This is a more traditional way to do these things. This is called a TLC plate. Little tiny thing, usually plastic backed with silica. But you put a spot here at the origin. This is a little line you drew. This is where the solvent went up. And your stuff can separate into a number of different things. For the calculation of the RF, we need the solvent front, which is the distance between where you spotted and where the solvent finally ended. And then you measure each of these distances. So let's just look at one of these. For example, the first one here. This is 5.5 centimeters up. Our solvent front is 6 centimeters. So to calculate the RF, you would take the distance that it traveled, simply divide it by the distance that the solvent traveled, do that ratio, and it's 0.92. That is the RF. If you have knowns, you can actually pretty much guess the nature of a substance based on its RF. Believe it or not, something as simple as this used to be legal for drug testing. I was actually involved in a case in that when I was in graduate school, but and we proved them wrong. But nonetheless, today the process for doing it is much, much more sophisticated. This is an example of a drug screen using what's known as high pressure liquid chromatography. So you have a column that's packed very tightly with an absorbent, and you pump liquid through at under huge pressure to get it through there. But because of that, you get really high resolution. This is HPLC, and again, you can separate lots and lots of drugs from a teeny, teeny, tiny sample. Using something called GC mass spec, where you do it in the vapor phase, you can even get much, much better resolution. So it's all basically the same principle, though, the adsorption versus the solubility. Any questions?
That was on Monday.
Yep, that was Monday. All right. First exam review. This is not going to be a long lecture, even though I'm going to stand up here and talk a lot. And the reason for that is that the exam is only 20 questions, number one. And number two, I want to drive home the point that in the hour or half an hour, whatever it takes us to go through these, that we can go through them and I can talk and talk and talk, and you still have lots of time. So when it comes time for the exam next week, don't worry about time, you've got lots of it. Start off with our first question. Mass of a sample is 5.5 grams. Which of the following expresses that in milligrams? Fairly simple conversion question. If we look at our word problem here, we can identify the given value, 5.5 grams. What we're trying to find is milligrams. So we want a ratio that's going to relate grams and milligrams. And grams must be in our denominator. Those are the rules. This is a ratio that works. There are 1,000 milligrams in every gram. So to solve the problem, you would start off with the given. We will multiply this by a ratio. You'll note that grams and grams are going to cancel, and we're left only with milligrams. Simply multiply this out, and B is the correct answer. Now, if you have any doubts or any problems or questions about doing this, just remember, this problem is based 100% on the metric conversion tutorial. Okay? Go to Chemistry Online. You can work these problems as much as you want. Any questions? Here's a table. We're looking for protons, mass number, charge, electrons, and neutrons for some elements. Start off with our first one. We need to look at our periodic table. This is magnesium. So we find magnesium. There it is, right there. Atomic number is 12. Now, we recall that the atomic number is the same as the number of protons in the nucleus. So our first entry here is simply 12. Any questions on that? Charge. We are given that we have 10 electrons, but we just determined we have 12 protons. Now the protons are positives, electrons are negatives. We have 2 extra positives, don't we? So this is going to be a +2 charge.
I had I emailed you for this exact, like this problem.
Mm-hmm.
And I put a negative sign in front of the 2,
Mm-hmm.
it marked me wrong.
No,
And
it will take.
well, whatever, I mean, I'm just saying, just for, it was correct,
Mhm.
what I had, but I just put the negative sign in front of
Mhm.
the number instead of behind the number, and it marked me
No,
wrong.
it will do it either way. I promise you. But maybe you put a space in or something.
No.
I don't know. Huh.
No,
I will check that.
yes, please, I put that in the email, that was the exact.
Finally, the number of neutrons. We know the mass number is 24. Remember, mass number is the sum of protons and neutrons. If 12 of those are protons, the other 12 must be neutrons. Any questions on magnesium? Lead is our next one. It's down here. its atomic number is 82. So that means 82 protons. Now, to get the mass number, we are given that we have 125 neutrons, we have 82 protons. Simply add those together, mass number 207. Now finally, the number of electrons. We are given that the charge is +3. Because our charge is +3, that means we have 3 more protons, 3 more positives than we do negatives. Therefore, the number of electrons must be 82 minus 3, or 79. Once again, if you have any questions or you want practice on a problem like this, here's a tutorial. Protons, electrons, neutron. It's not called that, but it should be. But it's there somewhere. All right, here we're going to take a name and we're going to write a formula. This is ammonium hydrogen carbonate. Now we remember that ammonium is a polyatomic ion. It's the only positive polyatomic ion that we have, for chemistry 100 anyway, and it is NH4. Has a +1 charge. We remember that carbonate is also a polyatomic ion. It's the parent of the carbon family. We know that because it ends in ATE. Carbonate has a -2 charge, and it's CO3. Now this is hydrogen carbonate. What that means is that simply there's a hydrogen attached to one of these oxygens. So it looks like that. Now when we do that, that changes the charge from -2 to -1. All right, how do we show that in our name? We simply stick the hydrogen in between. Now, just to make sure we're right, we can add up, make sure this is neutral. Ammonium is +1. Carbonate itself would be -2, but putting the hydrogen on drops that by 1, brings in a charge of -1, so this does check out to be neutral. Now remember, we have 3 tutorials for naming inorganic, ionic, naming molecular, and name the formula. So make sure you do all of these if you have any questions about the naming. All right, we want an atomic symbol here. Remember, the atomic symbol is simply the symbol of the element from the periodic table. As a subscript in front, we put the atomic number. And as a superscript in front, we put the mass number. So, if this has a charge, we show the charge as a superscript behind the symbol. So, here we have 18 electrons, 16 neutrons, a charge of -2. Step 1, how many protons do we have? Well, if we have 18 negatives here and a charge of -2, that means that we must have 2 less protons, 2 less positives. So instead of 18, we must have 16 protons, and that puts us here at sulfur. All right, so we start off for our atomic symbol by writing an S. 16 is a subscript in front, that's the atomic number. Finally, we have 16 neutrons. 16 plus 16 is 32. To show that this is an ion with a charge of -2, we stick it up here like that. Any questions? All right, density. We are given that we have a volume and a density. We want to calculate the mass. First thing you want to remember is just the definition of what density is. It's mass divided by volume. Now what we're looking for here is mass, right? So to solve this for mass, we would multiply volume times density, and that's what we would have. So all you have to do to solve this is plug in our numbers. 6.93 times 1.42. Do the calculation, and we get 9.84. Once again, this is a problem directly, absolutely directly from the tutorial. So if you need practice with this, go to the tutorial and do it. All right, which the following things here is not correct? PO43 minus is phosphate, persulfate, aluminum cation, oxide, or nitrate. This requires you to know polyatomics and stuff like that. Remember, you get a 3x5 card. You can write on one side of it. Put anything you want. If you're unclear on some of the polyatomics, just write them out. If you know them by now, don't worry about it. Don't waste the space. PO4 3- is phosphate. In the phosphate group, our two major players are phosphate and phosphite. They're both -3. This is the parent. Take one oxygen away, we get phosphite with the same charge. So this looks okay to me. Let's go down here to C. Aluminum cation. We look at our periodic table. Aluminum is there in group 3. Things in group 3 that form ions will be a +3 ion. So this makes sense. Oxygen is in group 6. Right over here. Things in group 6 will tend to gain 2 electrons and be a -2 ion. So oxide -2, that looks right. For our nitrogen family, we have two major players, nitrite and nitrate. Nitrate is the parent, NO3. Nitrite is an O2-, and they both have a -1 charge. So this looks right. That means that B is, of course, incorrect. Sulfate, SO4 -2. Sulfite, take 1 away, same charge. But per sulfate, we would add 1 with the same charge, SO5, not that. Any questions? Significant figures. We all love significant figures. Here we have a number. Step one, does it have a decimal point? That makes a difference, doesn't it? If it has a decimal point, trailing zeros are real, but leading zeros are not. Trailing zeros are part of the measurement, but the zeros in front are not. Therefore, we're going to get rid of the set of leading zeros, and we're left with 1, 2, 3, 4 significant figures. Another significant figure problem. We look at this and say, oh my goodness, how simple can this be? This is written in scientific notation. We remember, in scientific notation, all of the digits that are in the coefficient are significant. So all we have to do is count. 1, 2, 3, 4, 5, and there we are. If you have any questions on significant figures, please just go back and do the tutorial. Again, it will help you if you have any questions. All right, scientific notation. Here we have a number, and we want to correctly express it in scientific notation. Remember, what we want to do in scientific notation is to take our decimal point, whether it's real or imagined, and we want to move it so it's in between the first two real digits. In order to do this, here's our number. We want to take this, move it here between the 1 and the 3, and that's 7 places to the right. As we go to the right, that gives us a negative exponent. So this is going to be 10 to the minus 7. Because we have no trailing zeros after this, only the two significant figures here show up, and that would be D 1.3 times 10 to the minus 7. Of course, we have a scientific notation tutorial if you have any questions about how to do these types of problems. All right, electron configuration. The one on your exam is going to be different than this. Not going to have little arrows on it. It's going to be the compact version, but that's even easier than this. And we're looking for silicon. First thing we have to do is look at our periodic table and then find silicon. Right there. We note that it's in the 3rd period. Now that's important because that means that the first 2 periods are totally full. The first period can hold 2 electrons. This guy will have a total of 8. We'll have 2 here and then 2 here. We need to remember that these electrons go in one at a time with opposite spins and they pair. So for the 1s, the first period here, we're going to have 2 electrons, 1 up, 1 down. For the 2s, which is also full, we will also have 2 electrons, 1 up, 1 down. Over here for the p's, we have a total of 6 electrons, we would put them in one at a time with the same spin and then pair them. But they're all paired, so we have 2, 2, and 2. Finally, the third period. These guys are full, so that's an up-down. And now we have 1, 2 electrons in p orbitals. Remember again, they go in one at a time with the same spin. After you get 4, they start to pair. So we do this, up and up. If you have your sample exam, just put it in the stack up here. Thank you. Any questions? Of course,
And
that's
should
our
you-
questions.
I do have one. Should
Okay.
you put a 0 at that last box?
Nope, you don't need a
Just leave it
0.
blank?
Nope, nope. Just like in this. You don't put zeros,
Because some of it was
only
like,
ones and
touchy.
2s. Only 1s and 2s.
Yeah, well, some of them were touchy, that's what I'm making sure.
Any questions? We all love calculations. Please make sure you bring your calculator. Make sure you love your calculator so that you can use it and, appreciate it and whatever. Turns out that I found a stash of calculators from Triton. So if it's an emergency or you forget it or something like that, I'll probably bring 4 or 5 of these things. But you've never used these. It took me 15 minutes to figure out how to use it. And you don't want to waste your time. But for an emergency, that's an emergency solution. Okay, we could do this with a calculator in just a couple strokes. But let's do it the old-fashioned way, just to show that we can. First thing you would do in this, the old-fashioned way, is multiply the coefficients. And that's going to be 2.3 times 4.3, 10.1. Second, we're going to deal with the exponents. Multiplication, so exponents add. We have a +2 and a -12 to give us a -10. So we put the exponent and the coefficient together. We would get 10 times 10 to the -10. 10.1 times 10 to the -10. But this isn't in proper form, is it? The decimals should be between the first 1 and 0, so we have to move to the left. That's going to drop this by 1, and it's going to be 1 times 10 to the -9. Or you could simply use your calculator. Here's the tutorial. Lots of practice. And again, it'll explain to you how to do it. Physical changes. Physical changes are always accompanied by a change in state. Here's just a bit of advice for the rest of your life. If you have something that says always, that's always wrong. Okay? Because there's always an exception. Except that's an always, isn't it? Nonetheless, always is always wrong. Accompanied by a change of state, well, a change of state can happen. Having a little bit of a bump here. Change of state can happen, but certainly is not required. Remember, just taking gold and pounding it out thin is a physical change, but it's still solid gold. Physical changes result in the formation of homogeneous mixtures. What's a homogeneous mixture? Basically, it's a solution, isn't it? And a physical change never makes a new compound. It's always the same stuff. So that's wrong. Physical changes always produce new elements. Again, we have always. That's wrong. Only way to make new elements is a radioactive decay process. And finally, that means that all of these were wrong, so none of them are correct. We're naming P2O5. Whenever you have a naming problem, first thing to do is to figure out, is this molecular or ionic? We find phosphorus over here, oxygen over here. They're both nonmetals, so this is molecular. Why do we care? Because if it's molecular, we're going to use multipliers. Now, we look at this. We have 2 phosphorus, 5 oxygen. That's di and pent. So we're looking for diphosphorus, pent oxide. Phosphorus oxide, nope. Phosphorus 6 oxide, diphosphorus pentoxide. I think that works. Once again, if you need practice, P2O5, write the name here. How many oxygen atoms in copper 2 sulfate? Well, in order to do this, we need the formula for copper 2 sulfate, don't we? The copper, the Roman numeral 2 after it, means this is a copper plus 2. Sulfate, we all remember, is going to be minus 2. So we have a plus 2 and a minus 2. Copper sulfate is simply CuSO4. How many oxygens? Well, duh, it's 4. Any questions? Another density problem. But this one isn't a table, this is a word problem. Makes everybody nuts. But we are given a density. We're looking for a volume, and we're given a mass. So just like before, here's our formula. We're looking for volume, so we're going to move volume up, density down. It's going to be volume is mass divided by density. So all you have to do is take the given mass, 58.3, divide by the density, 0.841, and you get 69.3. If you want practice on word problems for this, density 2 has word problems. Some of these involve lots of conversions and stuff, but some of them are simple, and doing conversions is always a good thing anyway. Any questions? Lewis structure for BH3. On your exam, you will write a Lewis structure. And the artwork you present will be beautiful, right? Right. Think about it, okay? somebody's got to grade this thing. If it looks like you just kind of set all over your paper, that doesn't work. But if you write it out neatly and beautifully, even though it's wrong, if it looks beautiful, you'll probably get credit. So, all right, how do we do this? First of all, we need to find boron and hydrogen. Boron is here, and hydrogen is here. Boron is in the third group, so it will have 3 valence electrons. Hydrogen is here in the first group, it will have 1. So we start off with our boron, with its 3 valence electrons. Next, we're going to put our 3 hydrogens around it, like this. We need 2 electrons for every bond, so we just simply snuggle these up and convert the little dots here into the line bond convention. And this is the Lewis structure for BH3. Now you'll note that boron only has 2, 4, 6 electrons around it. Remember, we always shoot for 8. 8 is our octet rule. Boron is one of the exceptions for the octet rule. Any questions on how to do this?
Yeah. You have lines here. You want lines or dots? You want dots, right?
If we have leftover dots, we'll see those in a minute, then you leave the dots. If you use them for bonds, use lines. And speaking of that, how many valence electrons around the nitrogen in NH3? In order to do this, we need to draw the Lewis structure again. So let's look at our periodic table. We need nitrogen and hydrogen. Nitrogen is here. That's in group 5. Hydrogen again in group 1. We put our nitrogen in the middle. We're going to put 3 hydrogens around it. When we take these and snuggle them all up, we see that around this nitrogen, we have 2, 4, 6, 8 valence electrons. Now, if you were drawing a Lewis structure to be graded on, all of these electrons that are in bonds, these guys, and these guys, would be lines. You'd leave these guys just as dots. Any questions?
Where'd you get 8 from? How did you get 8 off of that periodic table?
Well, nitrogen has 5.
Okay.
So we started with our 5.
Right.
And we have 3 hydrogens at 1 each. That's 8.
Okay. It's just.
Oh, we're going to name K2O. First thing we want to do is decide, is this ionic or is it molecular? We look at our periodic table. Potassium is right here in the first group. That means it's a metal. So it is a not molecular compound, it's ionic, and that means no multipliers. Second thing we need to do is figure out if this is a transition metal. Because if it's a transition metal, we're going to have to indicate the charge. So we again look, we see this is in the first group. That is not transition, so we don't need the oxidation number. Okay, so we We have potassium and we have oxygen. No multipliers. What is it? Potassium oxide. If you want practice, of course, there's a tutorial for naming simple binary ionic compounds. Cesium is not transition metal, so we don't need charges, whatever. Any questions? And our last one here. Which of the following compounds will have a +3, well, the cation have a +3 charge? Simplest way to do this is to, again, look at your periodic table. Calcium, where's calcium? Well, calcium is right here in the second group. Now, what does that mean that it's in the second group? It means that it will have a +2 charge. So that's not it. Magnesium oxide. Look at your periodic table and find magnesium. There it is. Where is it? Oh my gosh, it's also in the second group. And it will also have a +2 charge. So that's not it. Ammonium carbonate. Now we saw ammonium half a dozen questions ago. We know that's a polyatomic ion, isn't it? And we remember that that's a +1 charge. And then finally, aluminum sulfate here, sulfide. Aluminum, where is it? There it is in group 3. Because it's in group 3, it will form a +3 cation, and that's the correct answer. Now I didn't even do E, did I? Why not? Because phosphorus and chlorine are both nonmetals. This is not an ionic compound. So there are no charges. Any questions? All right. Exam is next week, right here at 11. Make sure to bring your calculator unless you want to use one of those silly ones. If you noticed, so many of these questions came straight from the tutorials, didn't they? How about that? Practice the tutorials, you're going to do well. Tutorials that you get credit for are these guys. Please make sure you do them all. Wednesday morning, it shuts off. Wednesday morning, 11 o'clock, no more tutorials are allowed. And you will get 5 points for all the ones that we have accumulated.
Is that only up to chapter 4? The tutorials are only up to chapter 4?
Yep. And of course, we'll have more tutorials for the rest of the course.
Right. I was just the ones that would be shut down.
Now there was something else I was going to say. I remember it.
That's age, I know. I do it all the time.
Monday, yes. Monday.